you came to the deep dive on deep dive into Kubernetes scheduling, you're at the right spot. So this is going to coach you on running Kubernetes on top of vSphere. It could be useful if you're running in a VMware distribution, but this stuff also applies if you're running any other Kubernetes distribution on top of vSphere. Your speakers today are myself. I'm Steve Wong. I'm a software engineer with the Cloud Native Apps team at VMware. I came here from Los Angeles. I've been working on the Kubernetes project since 2015, and I'm chair of the Kubernetes VMware SIG, also lead of the Edge and IoT SIG. Michael?
Yeah, and I'm Michael Gasch. I'm based out of Germany, work for VMware as a platform architect, which is mostly field-facing work, doing architecture, design, deployments on kind of any Kubernetes on vSphere environments.
So you already read this abstract. If you're here, I'm going to skip it, but the only reason I left it in the deck is so that if somebody downloads the deck later, that they can scan that at the beginning and know whether they want to read the rest. This is the agenda for today. We're going to start with covering kind of Kubernetes default scheduling, how it works regardless of whether you're on a hypervisor platform or not. Moving into the zones feature that can be used with vSphere to get some valuable and enhanced features. Next, we'll go on to NUMA, and we'll explain what it is when we get there, non-uniform memory architecture. Michael is going to pick up and cover Kubernetes default resource management and ways of extending the default functionality of Kubernetes by utilizing vSphere features in conjunction with the built-in features of Kubernetes. Finally, I left it here. We've delivered this a month ago in KubeCon Shanghai and ran into the time limit. So I left it in the deck. If you download it later, we may or may not have time to cover high availability options. So let's move on to Kubernetes scheduling. What exactly does the scheduler do? Well, through the API, pods are created and they're placed in a queue. There's a beta feature that potentially can cause things placed in the queue to jump ahead of others, but you'd have to enable it. Then the scheduler, after they pour into this funnel, the scheduler continuously pulls pods out of the queue, looks at their requirements, and assigns it to a worker node, assuming you have more than a one-node cluster. When it does this assignment, it first goes through a stage where it filters out impossible worker nodes. These are nodes that couldn't run that workload, and these filters are called predicates. Kubernetes is very modular, so it comes with some default predicates, but this is extensible. So some of them are available off the shelf, open source, but you could write your own. So this initial filter stage, if you look at that picture, you see the X's over those, and those are just a determination by one of these predicates that there's no way that this pod is going to run on this node. Afterward, you're left with a list of eligible nodes, and in this case, it would be those orange ones. So we've got 6 possible nodes that are not, meaning they're not impossible. And there might still be preferred nodes to run those on. So this ranking is called priorities in the Kubernetes architecture. This, once again, is extensible. So there's a default list. An example of this is zones, which we'll get into in just a bit. But there are others. And like I say, you come with some of those enabled by default. Some are non-default. And if you want to, you can write your own. So after all of these stages of eliminating the impossible, ranking them, and jumping to a preferred order list, finally that pod is assigned to a node and is going to get kicked off and running. Now, I will say, I'll go into this is a deep dive. So in that ranking, if you have a very large cluster, the thing doesn't necessarily evaluate every single node. I'm talking like, say I have 1,000 worker nodes on my Kubernetes. The system, and this can be overridden, but by default, there's some number saying that if there's a humongous number of Kubernetes nodes, and I've got hundreds of them, I'm going to just take a percentage of these and rank those. And it's a latency concern. If you crawled over these, it just isn't worth it. And once again, you can turn off that behavior, but I'm just telling you, since it's a deep dive, that is something going on under the covers if you're running massively large clusters. So there are scheduling modifiers that can affect this. The first one is a node selector. And this is based on key value labels you put on the worker nodes themselves. Some of these are automatically created, but if you want to, you can annotate this with your own for whatever purposes you might have. Pods can define rules based on these node labels to achieve preferred placements called affinity. So the sum total list of the elements that influence these pod placements are labels on nodes, and zones is an example of this. Taints and tolerations, where you'd mark nodes with arbitrary labels which could correspond to a specific resource or whatever you like, that could either clue in the Kubernetes scheduler that I don't want to go to this node, or a toleration says, yeah, I'm, all things aside, I'm willing to go there. There are admission controllers, and a wide variety of these are available. An admission controller would take the pod spec and either validate it, meaning it's going to scan it for acceptable behavior, or potentially even mutate it where a pod spec might be missing material, and this would inject a default behavior. Why use zones? I'll turn it over to my colleague, Michael.
Yeah, just briefly. So, there's a question.
Yeah, would the taints and that be the approach that's being taken to try and deal with like GPU discovery and other physical device discovery, or
right.
Where does that fall in, if you know?
You mean discovery from the actual hardware perspective, or saving nodes from being scheduled by pods that don't use GPUs? Is that your question?
Yeah, the Google and a few others worked on something to do like GPUs.
Yes.
You know,
Yes.
and they came up with some new spec around that.
Yes, the device plugin.
Is that how they do that?
Yeah, right, will do. I just have to understand it first. Yeah, so your question is, if I'm using special devices like GPUs or FPGAs in my cluster, how would I protect those nodes from pods being scheduled on the nodes that are... Yeah, pods using that kind of hardware, making sure they land on that one, and protecting the nodes from pods not using GPUs, for example, to trouble the node. So you could do both. First of all, you could make sure that your pods using or needing GPUs could have a requirement, like a requirement on this kind of extended resource as a device plugin, to make sure they actually land on the machine, and then use taints to repel other pods that don't need GPUs or FPGAs to not land on that node, which are soft or hard kind of requirements that you can express, right? And so now your question might be, okay, why we are here in SIG VMware, why are we talking about scheduling? Because there's another SIG called SIG scheduling. It's important to understand that in vSphere, we kind of, running Kubernetes on vSphere, we have like two levels of scheduling or abstractions. We've got the vSphere scheduling, which is like DRS and the kernel. It's actually multiple layers there. And on top of that, we have the Kubernetes scheduler and logic. And probably you have other systems on top of that running. So we have multiple hierarchies of scheduling involved when running Kubernetes on vSphere. That could cause, if those layers of scheduling are not aligned to each other, that could cause undeterministic behavior. For example, until recently, until Kubernetes v1.12, we did not support the zones interface in Kubernetes. That means that a node would not express, a node running on vSphere, would not express that it's part of a certain zone or rack or whatever you want to define zone in that case. Meaning Kubernetes could not make use from a scheduling perspective to define like zone affinity or zone anti-affinity or node selectors or whatever Steve just has described. In Kubernetes v1.12, we implemented actually the zones interface, which is part of the cloud provider specification that Kubernetes has. So now you have the option to tag your clusters or A6i hosts or data centers. It's very kind of granular what you can do to define what a zone in your environment is. Because every vSphere environment is different. You're probably not running 3 data centers like in AWS or Google Cloud. So you could run like 3 hosts, which make up a zone, or you could run 3 racks, which could make up a zone, or you could have 3 data centers modeling a zone. So we implemented that in v1.12 to have like an arbitration and a knowledge sharing between the Kubernetes scheduling and the vSphere scheduler.
Okay.
Any questions so far? Just throw them in. I think we're pretty.
Yeah, and ultimately the zones feature is to spread things across failure zones, like automatically with you
Exactly.
minimizing the operational cost of achieving that. Now we're moving on to a subject called NUMA. What is it? Non-uniform memory architecture. When you're dealing with server-grade x86 hardware, multi-socket, those things are laid out in a motherboard. And between the sockets, you've got this pipeline drawn in red there. And you might have much faster access to the memory in the DIMMs near the socket as opposed to the one on the other side. The data, a workload running on either of these CPUs can still get to the memory on the other side. But in this case, and this varies by motherboard and chip family, but in this case, that bottleneck in the center there is 41 gigabytes a second. And there's also a latency penalty when you cross that. So you've got a scenario where when these workloads are laid down by Kubernetes, you'd really like to have an outcome where things that can fit on one side or the other actually end up running there. So why should you care about it? Well, nearly all database servers, the legacy transactional type ones anyway, like Oracle, but also MongoDB, present a workload that will opportunistically attempt to detect and consume as much as the system's memory is out there. And when these things get containerized under Kubernetes and scheduled onto some piece of hardware, and this doesn't matter whether it's vSphere or bare metal, that behavior can end up causing something to cross one of these NUMA boundaries. And it could be, depending on this caching situation, that you would be better off with a smaller cache that is higher performant than a larger one that really is sometimes highly performant, sometimes not, and you end up with non-deterministic behavior. These non-deterministic scenarios tend to be pretty ugly when you're in an organization that has to sign up for a specific service level agreement. So, Linux has some recognition of this. When it initially allocates a thread, it's assigned to a preferred node with default allocations from this. But there are some popular application runtimes like Java, at least Java pre-10, that don't respect a container resource declaration, go out and effectively get the memory quota from the underlying kernel, seeing the whole thing, rather than just the amount allocated to the container, and would attempt to go use it all. That maybe isn't preferred behavior. When you run Kubernetes on top of a hypervisor where you have the luxury of composing VMs that would carve this thing up in that drawing before, like split, many of these servers will obviously have more than 2 sockets, but if you were to carve this up into 2 VMs, the size of either side, you might be better off. Now, if you have monster workloads that in fact would suck up that whole machine, maybe you don't want to do this. But in many cases, you'll have clusters where, for efficiency in your data center, you'll be buying larger density machines just so you can fit more CPU cores in, yet you don't have workloads that hog an entire machine at once. You may be better off doing this in a way that would allow the underlying hypervisor to give you a hand with the non-uniform memory architecture. So how can these be avoided? Well, if you didn't have this, if you're running pure Linux, you can wrap an application in this NUMA ACTL, I'm not sure I'm pronouncing it right, to interleave memory. That's something where you're telling it just to get predictability that I want half my memory on this side, half on the other. And it's, you know, it's going to be bad half the time, but at least it's predictable. You know, you've interleaved these things. You can move to, for some of these application runtimes, if you're on the Java JRE, it turns out that they recently added enhancements. So moving up to JRE 10 might cause at least Java workloads to behave more acceptably. But sometimes this kind of stuff isn't available, or you're sucking in Java components that you didn't write yourself. You don't have control over that. Maybe in your organization, you've standardized on something else. And there are non-Java things that encounter this same kind of issue. There are active talks going on in enhancing these kinds of NUMA behaviors in the resource management working group, and get the deck later, and the link is live here if you want to read more about it. So you can use a NUMA-aware hypervisor to help you right now without waiting for these enhancements that are still being discussed. You know, assuming your workload fits, you make a VM as a walled garden sized right, you know, to an appropriate size to respect those boundaries. If you can't, there's some things you ought to do when you're laying out these VMs and laying out your pods to cause the system to not have a tendency to cross these boundaries. So don't declare things with larger socket counts than you need for your requirement. In general, never pick a VM with an odd number of CPUs. It's just going to tend to, maybe it won't cause a NUMA boundary, but even if it doesn't, it could tend to waste resources. But where it does cause one is you end up with this odd number CPU that appears to be available resource. The Kubernetes scheduler might think it can throw more in there, yet the only way it's ever going to run is to cross the boundary you don't want to be crossing. Never ever compose a VM larger than the number of physical cores. And if you do that, there are also some additional enhancements. Look at the deck later. Rarely do you need to change those, but the link is on the bottom of this page. So I'll turn it back to Michael to talk about Kubernetes resource management.
Thank you. Any questions so far on the NUMA thing that sometimes is a little bit hard to understand? Okay. So actually, just a note on the NUMA side, this is one of the most top 3 issues that I face in the field and working with customers, performance issues on NUMA. So, and we make it pretty easy for you, as Steve said, as long as you stay within the NUMA boundary, meaning look at your socket design, 2 sockets, 10 cores each. You'd probably define your VMs in a way that they are less than 10 or equal to 10 vCPUs there. So they nicely fit into a socket. That means vSphere, the hypervisor, presents a uniform host to the VM. So the Linux kernel wouldn't actually see a NUMA socket or layout. So it wouldn't actually have to handle and deal with the NUMA optimizations there. And you defer it to the platform, to the vSphere hypervisor. Moving on, another concern or a lot of questions or issues that I've seen in the field are around CPU, memory, and special devices, as already mentioned, GPUs in the field, running Kubernetes on vSphere. And starting with CPU and memory, in Kubernetes you express CPUs in millicores or cores, but then they are broken down into millicores. And millicores, they are a relative unit. They are not an absolute unit that you specify, meaning they can vary between the environments where you run the Kubernetes VM, the workers on top of that. So 2 cores on a AWS EC2 instance are definitely different than 2 cores on a GCP instance because they are just relative. Now in vSphere, we are not counting cores like internally. We're using megahertz in the hypervisor. So in the UI, you have the option to add cores, but internally they are mapped to megahertz, meaning there's already a little bit of difference going on here, which I'm going to touch later. And for memory, it's not a big deal because we also work with bytes. So Kubernetes has an absolute number of unit in here that you specify. And there are several other resources that you can specify, like already GPUs were mentioned, or FPGAs, or any other special devices. Some of them are not available on the vSphere platform, like for example FPGAs, mapping FPGAs through, or very specific network cards that we're not supporting on the hypervisor. So that could be an issue. For GPUs, we are usually pretty good because we work closely with AMD and NVIDIA, so we have good, decent GPU support. We're also supporting the NVIDIA GPU, a virtual GPU, meaning you carve up a physical CPU into multiple virtual GPUs and you spread them across the VMs. So on the GPU side, we are good, but for certain hardware, make sure that you're validated, you're tested, you have the drivers in the hypervisor. So in Kubernetes, then, a developer or a user or whoever can define requests and limits for each resource that you can specify in a pod. So for CPU and memory or your GPUs. For some of them allow different numbers, meaning that you can specify different number of requests or limits for CPU and memory. For GPUs, you have to set them to the same because the scheduler doesn't support overcommit on GPUs, for example. Now those requests are then internally mapped into Linux constructs, and they are mapped into the vSphere hypervisor, which we'll see in 2 slides. But generically speaking, you have some options to control the resource management side on Kubernetes, but you have to also make sure that Kubernetes runs on a shared platform, which is vSphere. And as we already said, there's a 2-level scheduling going on between the vSphere platform and Kubernetes, so you have to make sure that they're aligned. Unfortunately, there are often different goals that you want to achieve in a Kubernetes cluster. And this is from a talk that I gave in KubeCon Copenhagen earlier this year, going deeper into that matter. But just by having these controls of limits and requests, they are not always represent what your goals are when you run a Kubernetes cluster. For example, your priority could be running high utilization in your Kubernetes cluster. Or you want to be very fair between workloads, or you want to prioritize some of the workloads in the Kubernetes cluster. So you have to really think about how you model resource management in your Kubernetes cluster. And I'm just going to refer here to the talk that I gave at KubeCon. CPU and memory, when it comes to overcommitting, so you express more resources, you give more resources out to your developers than you actually physically have in your environment. Kubernetes has some protection mechanisms when it comes to overcommitment. But they are different between CPU and memory, because those are the resources that you can overcommit. For CPU, that's pretty easy, because CPU is a compressible unit, meaning if you overcommit in CPU and there's contention on that node, on the worker VM, the Kubernetes node, the kubelet, would start throttling. Actually, it's the Linux kernel starting to throttle your workloads. So you better make sure that requests and limits, you get them right for CPUs, especially for workloads that are critical, like your ingress controllers, your API servers, or whatever you run as a pod in Kubernetes. For memory, it's a little bit harder because we cannot compress memory. So in Kubernetes, the only mechanism to protect against memory overcommitment is to either get the requests right, so you figure out the right values for your workloads. But if Kubernetes has to act and decide that it has to kind of remediate because the cluster is overcommitted, then it has to stop workloads. And stopping workloads is based on certain priorities and functions in the kubelet in there. And typically, it's the one that's using the most resources versus the requests that are assigned to the workload. And stopping means your workload's getting killed, which is unfortunate for some workloads, probably. So you, again, get the requests and limits right, and we'll refer back to the KubeCon talk that I gave in Copenhagen. Now, as we already stressed, and I'm stressing this, running Kubernetes on vSphere is kind of the multi-level scheduling being involved here. And on that slide, you basically you see the hierarchies that those values of CPU requests and limits and memories are being translated into the Linux kernel, which is the kubelet in your case, the worker VM running on vSphere. And then underneath, you also have some controls on the ESXi hypervisor to control CPU memory behavior from a hypervisor side. Unfortunately, not all of them directly translate into the lower level primitives. For example, CPU requests from a pod spec manifest perspective, which says I request 2 CPUs, translates into CPU shares. Shares is not an absolute value, it's just a relative value. And if your host gets constrained, the number of shares are being used to determine whether your workload is getting throttled or not. So if you specify 2 CPUs as a request, that doesn't mean you're really getting 2 CPUs at the end of the day if you're overcommitting on the node. CPU limits are translated into a CPU quota. Now, the downside of using CPU limits is that you will always get throttled, no matter whether this host, the worker, is actually under constraint or not. So for the limits, you have to make sure that you set them right. If you set them too low, your workloads will always be throttled, which is not good, for example, for ingress or APIs. If you set them too high, chances are good that you're overcommitting your node, and then the node gets under trouble and is being oversubscribed. In vSphere, we have some controls. So we have CPU shares as well, so they would translate. But in the field, we advise our customers and users of Kubernetes on vSphere to use CPU reservation. Unlike the CPU shares in the Linux kernel, a CPU reservation is a guarantee that you give to your VM. So the ASICs hypervisor will make sure that under any cases, you will get what you specify in the reservation, and that's specified in megahertz. So contrast that with shares. Shares are just a relative weight when it comes to overcommitment. CPU reservations are a guarantee that you get from the vSphere hypervisor. And so for critical VMs, critical workloads, user-facing workloads, databases, whatsoever, we recommend setting 100% reservation for memory and CPU on that VM, just to make sure the hypervisor will always give you the resources that you need in case you need them. And you can still overcommit. That means you can run other VMs which are less critical with 50% reservation or 20% or no reservation at all. And if Kubernetes does not, if that worker, like the production VM, doesn't need all the resources, we give them to other ones. But if the production VM needs the resources, we reclaim them back via the hypervisor kernel and give them to the production VM. So mapping and understanding those constructs, requests and shares and reservations is critical to like a stable and robust Kubernetes environment, not just for the masters, but also for your workers. We're still good in time, so we can cover DRS and HA a little bit deeper here. So vSphere DRS, for those of you not familiar with DRS, DRS is a distributed resource scheduler, meaning it looks at the cluster of ESXi hosts, and it looks for balanced resource utilization of your VMs to avoid hotspots in your cluster, especially in cases when a hypervisor is overcommitted or there's a lot of trouble on one node. DRS will look like, by default right now, it's every 5 minutes.
Michael, I think we have a question in the back.
Oh, yes, of course. I'm sorry. The question is, does DRS require vSAN? vSAN? Was it? No. So yes, vSAN, the storage solution from VMware, is not required for DRS. DRS requires Enterprise Plus as a license, so it's not part of all of the vSphere editions, but it has no requirement from other products that we have, right? And so DRS is a kind of, as it says in the name, it's a distributed resource scheduler. You could think of like Kubernetes as well as being a distributed resource scheduler. So it looks at your ESXi host. It has no understanding of Kubernetes or the workloads within those VMs. It just looks for CPU and memory, and if you want storage and network contention, and then it tries to balance your cluster. So this is super helpful. But you also have to constrain it, meaning in DRS, it could happen that a VM on one host is being migrated to a VM on the other host. Now, without the zone support, or without any support to model your vSphere topology, be it racks or data centers, to the Kubernetes constructs like zones or failure domains. Without them, VMs could migrate in your cluster and potentially violating an affinity or anti-affinity decision that a Kubernetes scheduler has been made on top of this. As an easy example, imagine 3 nodes on the left are part of one zone, and the other nodes are part of the other zone. Without tying those things together, like vSphere informing Kubernetes that it has different topologies, a Kubernetes scheduler could schedule a pod on the same VM or on different hosts in the same zone, even though a user would have requested an anti-affinity. Because from a Kubernetes perspective, all it looks like for the virtual nodes, which is a VM in that case, those 2 VMs could end up running on the same ESXi hypervisor. In order to prevent that, we have some controls. With 1.12, we have the topology support in the vSphere Cloud Provider. We have DRS affinity groups, where you can model like those hosts are part of one group and those hosts are part of the other group. And then you can also specify anti-affinity and affinity between the VMs in your cluster. For example, you want to make sure that your masters, 3 masters, 5 masters, how many you run, that not all of them run on the same ESXi host. Based on DRS rules, you can actually model that. I do not see a lot of customers using those rules because they think that Kubernetes will figure that out. But if you don't tie those kind of two domains, like the vSphere domain and the Kubernetes domain together by informing them via the cloud provider integration, what could end up happen is like an outage because Kubernetes is scheduled to the same domain because it doesn't know there's different domains underneath. I think I have another slide on HA. Any questions so far?
Looks like keep going, Michael.
Yes, we're good on time.
Yes.
So this is just an image of how you would specify a anti-affinity rule or affinity rule for the masters here. So we've got different roles, and in this scenario here, we have modeled a fault domain, which is basically a rack or your zone out of those 4 hosts. They go in host VM rules, and then you can model your VM anti-affinity rules to put the master on different hosts, even in the same domain. So it's pretty flexible. It can get easily confusing and complicated, so we don't advise our users to use the UI and do it manually. We have in one of our CLIs or like SDKs, we have support for setting this programmatically, for example, as a post-deployment job. When you provision a VM, that after the provisioning is completed, you set the rules via an API call. And Doug is here, so I want to just give him a shout out. So GoVC is a Go binary. It's basically a CLI tool to set those things, and if you want to go crazy, we also have GoVMomi, which is a Go library where you can go way deeper than what GoVC does. But we have many customers who use GoVC to do the post-provisioning task to make sure the VM lands on the same or on different hosts, for example. One last comment on some things to watch out. The zone interface implementation is actually split into 2 phases. The first phase we implemented in Kubernetes 1.12 makes sure that if you run different host groups, like you have different vSphere clusters modeling your zone topology, be it a data center or be it a separate vSphere cluster, we define then a vSphere cluster or data center as a separate zone, meaning that those vSphere clusters don't know each other. Now, we've seen customers, or we have many customers, running stretch clusters, stretch vSphere clusters across 2 data centers, for example, where a vSphere cluster is kind of a large vSphere cluster, stretches across 2 different data centers, but it's still the same vSphere cluster. So we don't have multiple vSphere clusters in that game. Right now, that implementation that we did in Kubernetes 1.12 does not automatically support that topology. We have some workarounds that you can use if you're running stretch clusters, for example, like Metro clusters or vPlexes or whatever in your environment. So just like use that link or the number of the issue there, and you get some feedback, or our Slack channel for the VMware SIG, and we kind of give you some help in that case. But if you have the luxury of running separate vSphere environments, like separate vSphere clusters, then it's really easy to model the zones implementation as we did. So that is the phase 1 implementation. Another issue right now that we're working on is coming from that having separate vSphere clusters for your environment, you might want to have storage, dynamic storage provisioning, which is a nice feature in Kubernetes if you want to work with persistent volumes. Now, right now, the vSphere cloud provider does not support deploying dynamic storage or volumes in those setups where there's no shared storage amongst the clusters. Just to repeat that, if you have separate vSphere clusters or hosts, it could also be single hosts, and they don't share storage amongst them, in between them, like there's no NFS shared storage or there's no VMFS stretched across those nodes. Right now, it's not possible to use dynamic volume provisioning in Kubernetes. So we're working on that. That's just a logic constraint that we have in the cloud provider that we need to fix, and we'll hope to fix it in the next version. So those are the 2 major issues that, besides performance, I see in the field, and we just want to make sure that we prevent them by educating our user base. And there's workarounds for all of them. Not all of them are nice, but we're working on addressing that. All right, that's it from my side. I think we are good on time.
I think we have 2 minutes. I see a couple people poked in, but I think we have time for some questions.
Yes, so if there are questions, we're done.
We have one. Go ahead.
Yes.
Using the vSphere cloud provider, is it possible to target a storage cluster instead of just a single data store?
Do you mean what's the name for it? Data store cluster is the name, right? You have multiple data stores forming up a storage cluster. This is currently not supported in the vSphere cloud provider. It will, we're also working on that. We're working on completely revamping the way storage is implemented in the vSphere cloud provider right now. And you might be also aware of the transitioning from the in-tree cloud provider to the out-of-tree cloud provider, which is also an undertaking that we are working and being involved in. So, and the container storage interface, CSI, eventually like just G8, and so we have now kind of more flexibility and freedom to implement that. But right now, on your question, it's not supported to run data store clusters for storage. Good question. Yes. Yes, the comment was the CSI driver does support data store clusters, but it currently not supports the in-tree cloud provider.
Any last questions? Otherwise, if we do run over, we can take it into the hallway. But I think we have time for one more if anybody's got one.
Yeah, okay. No worries. Yeah.
Okay, thank you for coming.
Thank you very much.
Oh, by the way, let me throw out one other thing. As part of Kubernetes itself, we have a bi-weekly VMware SIG meeting. And this is a thing where we have developers of the cloud provider, the storage plugins, as well as users. And we have guest speakers. It's a Zoom meeting. You can join the group, and I'd invite you to do that. If you're just catching up now, the notes from the past meetings are a rolling Google shared doc, and the videos are uploaded to YouTube. So if you're using Kubernetes on vSphere, by all means, join the group. We also have a channel on Slack and a mailing list. Once again, thanks for coming. Yeah.